So let's just start now, try to simulate a solar thermal system. So in order to start doing the simulation, as we discussed during the PV module simulation, what you need to do, you need to start from the wizard tab. So if I click here, now I have to go to the template, and now here I have to define my available templates, again based on the system that I'm looking for now. So in this case, because we are not looking for the photovoltaics, so we're gonna put not applicable, and now the system numbers are reduced. Solar thermal, yes. And now we have, say, 6 templates available. Then what we're gonna do, we could, for example, for now, just to keep it simple, electric consumer not applicable, and then domestic hot water, yes. Now I have different systems, as you can see here. I leave the rest as it is. Now I would go with the most simplest one, so space heating or hot water. Let's go with hot water because it's the most simple one. Then I'm gonna click on continue after selecting my template. Now here I can define for now some rough numbers and values. So number of the persons that they are living in the property, or the temperature that we are looking for, or the daily hot water in terms of a liter, and then also the pattern. So we leave it as it is for now. Then later we can edit in our uh, system diagram. Now we click continue as it is. So here, very similar to what we have done on the PV panels. So we have different standards here, European, North American, and Chinese standard. We keep it as a Europe. And if I want to select collector, very similar to the PVs, I need to look at the catalog here. And in the catalog, you see different variety of solar thermal collectors. A point that I would like to mention here is that, as you can see, the data source of the data is these are from, for example, SPFs, and also if you scroll down, you have different uh, standards for testing the solar collectors, like solar key marks, etc., etc. So what is also, so it means that all the data that we have, as you probably remember from our sessions, is we were talking about zero optical efficiency values, as you remember, and then A1 and A2 values for efficiency curve. So we can look at those values over here and select our collector. And all of these values also has been reported by the data source that is mentioned here, and these are not from usually from the data sheet of the providers. So it's more reliable information. If you are looking for the most reliable ones, probably you could go with the ones that has the solar key marks on them. For now, we keep it simple, flat plate, good collector. We click OK. And similar to the PVs, again, if you are dealing with a collector that you don't have it in the catalog over here, you can add this with similar method, copying the mark line and then change the mark line. So we keep it as a flat plate, good quality. Same to the PV, orientation, tilt angle, same as it is. And uh, so this number of collector, it basically comes from the values that you have in the hot water demand here. Obviously, it is suggested by the Polysun, but you can also override. So you can put 4, 5, and also you can work on this number later in your system diagram when you have it here. What we need to do also mention here is that recommended tank volume. So as you can see here, we can't overwrite this value, but if we want to change this, again, this one is recommended by the software based on what we have in the hot water demand. But if I want to change this tank, I can, again, open the catalog of water tank and then look at the different water tanks that I have. Even if I want to set them based on the volume, I can click on the volume and I can see from 113 up to 10,000 water tanks. So you can select whatever you would like if you want to overwrite the values that is recommended by Polysun. We keep it as it is, then continue. Now I have also the heat generator. So recommended power, for example, is 6 over here. So I can even, again, change this value or pick the one that I would like to have it myself. If I want to do that, I can open the catalog over here and then again look for uh, the boiler model or basically the heat generator, could be even the heat pumps that I'm looking for, I'm interested in. For now, we keep it, as I said, as it is, and then accept. What is going to happen now, similar to the previous one, Polysun is going to run the simulation. And if you look at here on the bottom right corner, then you can see in a very short period of time a green bar that is completing, and the simulation is now moving forward, and we should have results. So similar to the PV, now we have a result overview, which we discussed that it's just the overview of the key results, but we're not going to work with this in general, and we need to, again, similar to the previous one, go to the result tab and analyze the model in more details. We're going to close this. And as you can see here, and you might notice the difference, now we have more components and it's more complex than the PVs. So what we can do, we can also modify all of these as we did in the PVs. You have also, similar to what we have discussed in the PV, has the option to select from the other standard templates, other systems. So you might look, for example, let's close this photovoltaic one, and then we can open. So this is, for example, domestic hot water system, only domestic. This is a space heating system, only space heating. So, but also, for example, you can go with domestic hot water and a space heating system as well. So if I open this one, no, if I scroll down, I can see different systems. I might, for example, go with one of the simple one for now, and then move forward with the more complex ones. For example, this one uh, could be okay because it has a space heating, so solar thermal, and then in addition to the hot water that we have selected here, this is only hot water, as you can see. I have just only the demand for the hot water, but I can also now go and select the one that also has a floor heating system. So if I double click on it, it's going to ask me if I want to add this to my system diagram. I click yes, and then okay, and it's going to pop up over here. So as you can see here, now I have a demand for hot water, as you can see, and also floor space heating as well. What could also do is that, for example, I could, so this one is also with the solar thermal, as you can see, but I might go completely without solar thermal. So I can select, for example, this one, which is a space heating with the heat pump, only heat pump. If I double click on that in order to add to our system diagram, similar way, it's going to ask me the question if I confirm. Now I have only heat pump, which is basically is a air to water heat pump with the controller. Now I have hot water demand and also uh, floor heating for the build. Also, for example, I might also go with the other system, which is more complex. For example, this one we have covered in our heat storage session. So this one is basically ground source loop with the heat pump application for both, again, uh, space heating and hot water. So as you can see, I can add different systems and then later maybe do some comparison and work on that. So various systems available in the library for you. But what we are going to focus right now is going to be more on the demand side of the of the system. For example, here, as you can see, I have a building, which I could, as you remember, I could identify different scenarios. So as I also mentioned, for example, everything that is here, you can double click on that, and then you have availability to modify it. Or even for example, the pipes, you can double click on that. You can change the type of it, for example, if you need to see it in the report. How's the environment, for example, the dimension of the pipe, uh, even the type of the pipe as well. For example, here you can select if you want to go with the copper, steel, if you want to go more in details. Or even, for example, here, as you remember, we select the boiler. What I can do, I can even change it from boiler to the heat pump, and then select the type of the heat pump that I would prefer to have. So as I said, different ways to do it and different modification you can uh, implement in your default system there. You probably remember from our introduction that we could have, for example, systems with pool and also maybe district heating system. So for example, if I go to the pool heating system here, I have different system which is integrated with the pool heating system. So I can select one of these as an example, because as you can see here, it has all type of the demand almost. So it has the hot water demand, it has a floor heating demand, and also the pool here. So I can double click on that, similar to the previous one, and then add this to my system diagram. What also you might remember from our solar sessions is small size parabolic trough collectors or other uh, process heat applications. So with the Polysun, you can also do simulation on those as well. So if I navigate through the standard templates, I could find solar process heat, district heating. I can open this one and then probably select process heat solar term, which basically use with the solar uh, solar energy inputs, and then I have also process heat application here. I can double click on that, and then I can add this to my system diagram as well. So as you can see, now I have possibility to maybe make a comparison between all of them, similar that I've mentioned with the system comparison over here through the results. What I would like to do now in the space heating and pool, starting from the most important part, which is the demand side of it. So as you can see now, if, as I mentioned also before, I can double click on everything and I can basically uh, work and modify on that. If I double click on the hot water demand side, uh, now in this window, I have all the information related to the hot water demand. Uh, Starting, for example, from temperature, you can set any temperature you want. Usually it's 50, 55, or at most like 60 for hot water demand in the houses. So we leave it as 60 as it 50 as it is. Here I have different months, which all of them has a similar value of 300 liter per day, which means that in this month I use the demand for the hot water is like 300 liter per day. I can modify this to any value like 600, for example. It's going to ask me if I want to copy. So if I click yes, it's going to copy on all months. So look, if I click yes, now it changed to change all other values in the other months as well. I can put lower value even. So let's put, for example, 200 and click yes, and all the values are now modified. So in January, on a specific day, it's 200 liter per day. If I want to go more in details, for example, similar to what we have done in the PVs, I can also work on the daily profile. If I double click on that, now I have a daily profile catalog, which has different types of it. And as you can see here, I have all the 24 hours of that specific day. So hour 1 to hour 24. And the values that you see in the table is basically is a percentage. So it's basically the percentage. So if it's 200 liter per day on that day, for example, if I go with the multifamily house, on hour 7, I use 10% of this 200 liter per day. So which is 20 liter. And then on hour 8, again, I use 10% of 200 liter per day, which is 20 liter. If I click this one, it's going to be selected as my profile. What is also important is to, for example, mention is nominal flow rate, which means the flow rate of the hot water usage. So if it's automatically defined by Polysun, but if I want to modify this, I can say no. And here I have the value. So nominal flow rate, any value I can put. For example, if I put 600, it's going to be 600 liter per hour, which means that uh, per minute is something around like 10 liter per minute. So 600 liter per hour divided by 60, it's going to be 10 liter per minute. And 10 liter per minute is going to be my value basically for my flow rate value. If I go back to this one, which is 20 liter per day, and remember that number, if I go back to here and see, for example, on hour 7, I have 10% of this 200 uh, liter per day, which I mentioned is like 20 liter per hour. So now I have a 20 liter per hour with the flow rate of 600 liter per hour. I'm gonna have, or 10 liter per minute, I'm gonna just only have 2 minutes of hot water usage on that hour, and the rest of that 558 minutes is gonna be no usage for hot water. So this is the way that Polysun works, which means that if you put these values, this is the way Polysun deals with the simulation. So it's gonna do the simulation for 2 minutes only, and the rest of that period of time, 58 minutes of that hour, nothing is gonna be simulated. So we can also confirm these values, as we mentioned about this 20 liter per hour, which is gonna be equal to the 2 minutes of the consumption of hot water on that specific hour. So for example, on hour, which means that here, what I dealing with these numbers means that on hour 7, I'm gonna use hot water for just only 2 minutes, and then I'm gonna use hot water for only 2 minutes in hour 8. If I confirm this and then confirm this, Polysun is gonna ask me if I want to copy the same consumption profile to the other system with similar hot water consumption pattern. So if I want to make some comparison, I usually put yes, and then those values going to overwrite in the all of these systems on A9A, for example, 16 in any system with the hot water demand. The value is going to be overwrite and copied to all of them as well. But for now, I don't want it to do that, so I say no. So I want to now check about that uh, 2 minutes of usage of hot water on hour 7 and hour 8. How can I do? I can go to the results, then simulation analyze. It's going to ask me to save the project. I could say yes. Now I have this window open here, which basically shows me what happens in the single time steps of simulation. So if I move this to the right, you can see that now the values are changing, and it shows me every value related to the simulation on a specific component on that specific time steps. So I can check, for example, how much is the water temperature, hot water temperature on January 1st at 4 o'clock in the AM. Even I can look at my storage tank model, which usually is a 12-layer model. So I have a 12 layers here, which is more related to the advanced course, and then you can do the modeling on your storage tank as well in terms of the temperature in different layers. So I have 12 layers, and then you can modify and work on this storage tank model. What I need to remember now, and it's important for me to check about that 2 minutes of usage of hot water. So if I move to the hour 7 and 8, so here, this is hour 7, yeah? So on 6:57, very close to the hour 7, as you can see, I don't have any water flow. It's 0 liter per hour. Yeah. If I move this to the 83, now it's the beginning of the hour 7. Now I have 60 liter per hour on 7 o'clock. And then I have it still on 7 now. On 7:02, now I don't have any again. So I just have hot water for 2 minutes. And once that 2 minutes is finished, then I don't have any hot water flow rate here. I can continue. I'm not going to have anything until 8 o'clock. So 7:57. Then on 8 o'clock, now again, I have this 600 liter per hour. Now what's going to happen? If I move forward, I'm still have it. And after 8:02, again, I'm not going to have any hot water demand here. So similar to this, you can work on your simulation and see all the results related to the system. I can close this, and now I have, again, very simple representation of my system. In this system diagram, so I have floor heating as well, so which basically deal with the heating, or it could be also cooling element as well. So I can have a floor heating, I can change it to the different radiators maybe, or different scenarios as well. So it can be done. What else I can do is working with my building. So these two are completely separate uh, systems as hot water as well. So you can have a different consumption and demand in the hot water, and then also the specification of the building could be also different. If I double click on the building, now I have the settings or window related to my building. So I can, for example, define the dimensions of the building based or orientation of the building depending on my case. And for example, if I want to have this in the report, if I want to add any description to my building, I can add it here as well. How Polysun works with this building component in the simulation, it has two ways. One of them is if we know exact demand of the building, so we have it from a client basically. So we put this as it is. The other option is that we don't know the demand, and Polysun is going to be automatically allocate some number for my heat demand. So I have two options. So if it's not known, as this case, so basically Polysun is going to do this calculation for me for the demand. What I need here is probably maybe I can define the building. So if I open the catalog, now I have different buildings. So I can look for the building that is close to what is my ideal case, closer to my case is. So for example, it could be a German house, it could be office building, it could be even a single family house as well. And I have, for example, different U values of the building. Remember from our first session um, on the U values, that how much is the total U value for a building. So we can basically define that, then specific heating power of the power demand, watt per meter square. So, and all the informations, for example, defined for that specific type of the building. I can select, for example, because this one is a low energy building. So even I can go with, for example, higher energy buildings or passive buildings as we discussed in our passive design. So different options are now available for us to do that. I'm gonna go with the single family house, low energy building. And this would help me basically to define my case. What I need here usually is the size of the house, as well as the U value, the total U value of the house. As I said, I can define the dimension of building, the orientation, number of floors, etc., etc. here. And if I click OK, it's gonna have there as well. What I forgot to mention, probably also in the hot water demand, is the absence. So the absence means that if I click here, I can define for example, in the building case, I can define on which specific days or patterns I'm not going to be at home. So maybe I don't have, uh, I'm always at home, so never. On Sundays, I'm not at home, for example. So this is the absence. Weekends, Monday to Friday, for example, if it's a holiday property. So I go just in the during the weekends. I can put Monday to Friday. So it depends on the pattern. So you can define where when you are absent from the building. Yeah, you can have them at here as well. You can also have this here in the temperature side as well. If I go to the temperature side, you see I have the absence here as well. If I click here, again, I can define when I'm not using the hot water. So imagine if it's a hotel, that would be different because, for example, the peak during the summer is higher or lower, or even like, for example, if it's as I said in previously, if it's a uh, holiday property, so uh, I'm gonna be there only on weekends, so Monday to Friday, I'm not gonna have any water consumption here as well. So it has the availability to have this, and I would expect you guys to consider this when you are doing your assignment as well. I click OK, and now I have the system over here. Now what I can do, I can run the simulation in order to see the values that I have. If I go to the component results, now I'm gonna have the results over here. With all the information, I can take a look at the, for example, on the collector, what is the mean temperature of it, the flow rate in the collector, and all the information, collector field yield. So all the information is basically here. If I go to the building, which we were discussing, I can look at energy I'm getting from, for example, the collectors, total energy loss that I have, or all the values that we have discussed and we have now has been simulated in the Polysun. The most important probably is the heating energy demand of the building, for example, as you can see here. So I can check if it matches with what I'm looking for or not. But I can also take a look at here. I mentioned it here. For example, you can set your heating set point temperature for day and night. So you can put maybe other values here and it's going to affect your system in general. And that would be, for example, you can even, for example, define your warmest months. So this is what usually you deal with, and it's going to affect your final results. As I mentioned, this is the first method, which you just know the U value, the total U value of the building, or even if you don't know, you can go to the catalog and then you can check which is similar to your system based on the U value of the building, total U value of the building, and then you can define the dimension of your building based on these values and the number of floors. So if I click OK, and then I can see basically the component results for this case. It takes some time to do this simulation, so you need to be a little bit patient for that. Now I have all the results and I can double check and also have an overview of the results, especially, for example, in my building side, as I mentioned, all the values over here to see if it matched with what I was expecting. As I mentioned, if I go back again to the building, um, now we were covering that we don't know about the energy demand. If we know energy demand in somehow and click yes, this is the second way that we can define our building. Now I have selected now the energy demand yes as known, and now I have different ways to do it. So it is a heating system. So imagine I know, so if I go to the energy consumption known, so how we know this, it could be, for example, as annual. So I put, for example, this is annual total heating energy demand. However, if I want to go a little bit more accurate, I can go with the monthly energy demand. So this is the monthly energy demand that I have with their specific values and losses and etc. etc. What else I can do? I can also go with the other way, which means that, so for example, if I just know, so I can put here, for example, for different months, January, October, November, even in summer. So as you can expect, during the summer, is the value is lower in terms of uh, demand, and also energy losses. Again, during the summer, it's lower. What I would like to also mention, if that's the other way, is to define this based on the fuel consumption. So if I have, for example, have some ideas about it based on the firewood, electricity, gas, I can put here, and Polysun will try to automatically match this. Uh, so this is just something to define the specification of the building. I'm not going to confirm this because the one that we have already selected is the more accurate one. So now I have this, I can define this. As I said, I can define the specification of my heating and cooling element, how it works. Yeah. For example, because it's a floor heating, it's a nominal inlet temperature, outlet temperature, everything is now automatically calculated because this is the device that I'm dealing with. And now we can go also to the pool. And in the pool, if I double click on that, I can define if it's an outdoor pool, if it's an indoor pool, how much is the temperature setting for that specific pool. I can also define, for example, the dimension of the pool in terms of, for example, the dimension, as I said, length and the average depth. And the volume is going to be automatically calculated based on the values that I put here. The U value of the wall, so I can define it in a different ways here as well. So for example, here in the pool, what I can do, I can look at the cover side. So if it's an outdoor pool, so obviously it could have a cover, which means yes. What it means in general is, for example, here I have opening of the pool. I have also closing of the pool, which means that the pool opens at 9 o'clock in the morning and closes at 7 p.m. And then I have the opening of the pool, day of the year, so 120. So January, February, March, April. So it's gonna open by the end of April, and then it's gonna run from day 120 until day 275. You have some uh, values here, which is related to the outdoor pool, which is, for example, is a wind fraction, and etc. etc. I can also change the pool type to the indoor pool. The values is going to be almost remain the same, with the only change that now I'm not dealing with the outdoor condition. I'm dealing with the indoor condition, like room temperature in the indoor pool. I have to define them as well. So this is all I have. So in this system, I have covered all the main three consumers. I have covered the water, hot water demand, heating of the building demand, and also I have defined the pool for my system. So if I'm dealing with the domestic system, this is usually all I have to deal with in the consumption side. And now let's move to the process heat application. So the last system we're gonna cover is gonna be the process heat. So if I go to the template now, instead of in a comparison, instead of this case, which I had, for example, consumers as or demand as a hot water demand, heating building demand, and then swimming pool demand. Now in here, I have now process heat. So if I double click on that, so how process heat works, basically, let me show you here. So I have a higher temperature heat input to my process heat. Then it's going to be used in the industry for process heat application. And then I'm going to have an outlet with the lower temperature, which we usually call it as energy sink. If I was using, for example, on the other side, process heat as a waste heat input to the system, that would be energy source, which again, the the temperature is going to be different than this the condition. So if I open this one, which is basically energy sink and source component, now as you can see here, I have an inlet temperature, as I said, higher, 100 degrees C, and then the outlet after using it in the industrial process, whatever, I have 80. degrees C. So obviously the power is going to be negative because it's going to be used in the industry. Similar to the other consumptions, I can also define, so this is a very simple actually, this definition, but I can also define the user profile. So if I go to the user profile and set yes, now instead of temperature, inlet, outlet, and amount of the heat sink, now I have profile. I can double click on that. Now I have different profiles. Again, CSV file, if I know the process, how it works in the industry, I can import them to the system and then use it to simulate my industrial processes, basically. So this is all you need to know about the system. So we start with the PVs, for example, then we went to the PVs with electric cars, then hot water, only hot water system, space heating and hot water, and space heating with the heat pump, for example, here. And then we covered the most comprehensive one, which it has hot water demand, space heating demand, and pool as well. And now this is also the process heat, which you can use these components in a different phase to simulate different system. As I said, even you can use something similar for waste heat recovery by moving this component to the production side and start to work it out. How this system works is basically I have a solar field that helps me for the system for the hot water in the simple hot water solar thermal. And I'll have also the boiler as we discussed. If I click on the boiler, you see the specification of the boiler, and then I have the controller. So each component here has its own controller. So this is the pump. This is the pump controller. This is the boiler or heat pump controller, and this is the three-way valve controller. But if I go to this one and double click on the heat pump controller, I see that boiler, sorry. I see that this boiler could be also the heat pump. I think I see that this is the pattern that this controller works, which means that it switch on availability times at 6 o'clock, 7 o'clock, and 8 o'clock, Monday to Sunday, and from January to December. So this is how the controller controls the boiler for me in my uh, hot water system. So if I run the simulation now, I go to the system results. Now, here is the results that I have, and the most, maybe 2 or 3 most important information here is QDEM here, and then the QUs here. And what does it mean basically? So QDEM, as you can see here, is the how much energy we require in our system. So this is the demand, so total demand per month, as we discussed. And then the QUs is basically how much energy that we actually consume during the whole year or during the basically the period of the time. Could be January, July months, or annual values. So these two values, as you can see, are slightly different, which is almost acceptable for me. It's not that much different. But let's say, so this is the reason why I don't have any error. Let's make this time a system with the error, yeah, intentionally. So similar to previous one, I'm going to copy the system diagram here. And now I have a new system, as you can see here. Now what I'm going to do now, as different to the previous system, is that I'm going to open the controller here for my boiler. And what I'm going to do now for the boiler now, I'm going to turn off the boiler. So it's not going to work at all. So the whole system now is going to be dependent on the solar field. So let's see if this system works, and if it works, if it meets the demand or not. So I'm going to do the system results. I'm going to wait a couple of seconds to simulation to run. As you can see, now I have an error. So it says that energy demand for domestic hot water not met, which means that the system now is not capable of providing the enough energy for the system. So if I go and look to these values again, as I said, QDEM and QUs, now you see a huge difference between these two, which means that I have the energy demand is 3,456, but only I use 1,995. This is very important because this is the how we usually design our system. So if I go back, yeah, it says there is a problem with my system, the warning, I close the warning, I go back to the result. This time I'm going to the component results. Yeah. And in component results, I'm gonna now discuss to see what I can do in this way. Yeah. So here, if I go to hot water demand tab, now you can see the same expressions that we have. So for example, total energy demand, which we called it as a QDEM here, and then also total consumption as a QUs. And you see now I have also another parameter called energy deficit, QDEF, which means that basically these amounts is missing from my system in terms of the energy demand and energy consumption. So you see that I have now a difference between these two. So 317 minus 112, for example. And this is the amount that actually is missing from my system. If I close this window and now go back to the previous one, the one that its boiler is also on and working 3 hours per day, every day for during the year. If I go to the results now, system results, you see these value. One point that I would like to mention here is that solar fraction is 53.5. If I go back to the previous system, when the boiler is off, all of them is off. Now, if I look for the system results, you see that the solar fraction is 100%, which is true, because here the boiler is always off. Coming back to the original system, when I have the boiler for 3 hours, now what I'm going to do, I'm going to go back to the component results. And this time, I'm trying to go to the hot water demand tab. And now here I have again energy demand as a QDEM, energy consumption as a QUs, and Q deficit. Uh, you might also here ask question, uh, why these two values differences is lower than 157, so it's around, like, let's say 35 from here and then 56 from here, around 90 kilowatt hour, so it's not 157. And why is the reason? Because so uh, the reason generally here is that so the energy deficit can't be compensated by. So imagine if you have a 2, 3, 4, 5 time steps of the simulation. In the first time step, you have an energy deficit of maybe 7 kilowatt, and then in the next time steps, you meet the demand and also you overproduce it. But in the third time step again, you have an energy deficit of 8. So 7 energy deficit on time step 1, 10 maybe extra in time step 2, and then 8 deficit on time step 3. So in this case, because energy deficit can't be compensated by the following time steps that are higher or meeting the demand that is more, then the energy deficit can be reduced. So in terms of the energy deficit, it's gonna be 7 plus 8. So 8, 15 energy deficit. However, because we can't include that 10 extra production in the second step. So that's the reason why here the energy deficit number is not matching with what we have here as well. Okay, for this system, if I go to system results again, so now I have to review maybe in more details the parameters that the simulation results is going to give me. So the first one that I'm going to look for it is ESOL, which is very similar to what we have discussed in the PV panel. So this is a total solar irradiation onto the collector area. This is the total value, and these are the monthly values. Obviously, during the summer, it has a higher value. So, and then if we consider what collector basically converts to the useful heat to the system, basically, it's going to be Q sol. So, solar thermal energy to the system, 2,345. So obviously uh, lower than the ESOL, and you can, from this, you can get the efficiency of the collector somehow. And then from QSOL, you also have SSOL, which basically means that how much of this value goes to the tank. So solar energy to the tank, 2081. And if you compare these two values, 2345, you have some losses because of the system that you have from solar collectors to the tank. So these are for solar collectors here. And also I have similar uh, parameters for our auxiliary system. So in this case, I have a gas boiler here. So in a gas boiler, I'm going to have exact same similar basically parameters as well. So I have, for example, uh, instead of ESOL, now I have EAUX auxiliary. So in this case, it's our gas boiler. And then what else I have? So similar to the previous one, I have also Q auxiliary. So he basically that heat that transferred to the system uh, from our gas boiler. Yeah. So this is the Q auxiliary aux. And then the next one is gonna be basically instead of S sol, yeah, that we have, now we have SX, which is related to the auxiliary system. So energy from our gas boiler in this case to the tank that we have, which is going to be again lower than what we had in QX. So if I look at the QX number, 1,828, now is 1,811. So heat loss here is slightly lower than what we had in the solar part of the system. Other important parameters could be solar fraction, which is basically what we have discussed. So solar fraction of the solar energy to the tank, as you can see here, I'm trying to, yes, that's much better. So I have fraction of solar energy to the tank as SFI. So basically it's S sol, what I have here, solar energy to the tank, divided by S sol plus S aux from the auxiliary. So SFI is basically S sol divided by the addition of these two values together. Then I have also solar fraction, fraction of solar energy to the system as a SFN, which basically is a Q sol this time as a solar thermal energy to the system. So divided by Q sol plus Q auxiliary. So we call it SFN. And also I have SFG here, solar fraction, fraction of irradiation in collector plane. So which is basically the ESOL, so irradiation onto collector area, divided by ESOL plus E auxiliary. So these are basically our different solar fractions numbers as well. Obviously, you can close this, you can go to the component results, and then you have more detailed information about the components in terms of the temperatures you want to look for them, or all the information that you have for the system. What we're gonna do now is try to follow the same steps that we did with the PV systems. I'm gonna go to the results, and this time I'm gonna go with the graphical evaluation. Very similar to what we have done with the PV system. Now, what I'm going to do now, I'm trying to understand how well my collectors and the tank is working together. what I'm gonna do, I'm gonna add curve as similar to the previous one. I'm interested to know basically production of the heat from my collector, Q sol, as we discussed. So collector field yield, which is uh, watt. So I'm gonna click OK. I'm gonna have this. I forgot to put the week, so I'm gonna put week 12 maybe. And what else I'm gonna add? I'm gonna add storage tank. So in the storage tank, remember that I've mentioned something about the different layers of the storage tank. So I mentioned that we have 12 layers. So starting from bottom to the top layer, I'm gonna pick one of the bottom layers, layer 4. And also what I'm interested to do as well, I'm also interested to see about the top layer, for example, to see what happens between these two layers to each other. So I'm gonna select top layer as well. Now, what is here is different between this graph and the PV graph is the units. So here I have a watt for collector field, but I have a temperature degree C for storage tank temperature. So what I can do in the axis part, I can change the axis for the temperatures. Now the graph is more uh, understandable, I would say. I can also change the color. I would put this one black, this one maybe somehow, I don't know, green, and the other one I can put from the previous colors. I can also optimize the scaling a little bit, and now it should be okay. So what it says actually to me is that, so as you can see, so collector somehow is working in this specific day very well. But however, here, for example, I don't have that much of a solar uh, energy coming from my collector. So what is going to happen? Probably I am going to have a lower temperature for uh, for my water tank at layer 4, but top layer is going to remain almost the same as it was. And you might ask the question why this behavior we have, and it usually comes from that we have this gas boiler here, which helps the system, especially the tank, at the higher levels to maintain the temperature, even on the days that we don't have really sunny days. As you can see, a lack of sunny day probably, and what's going to happen? A sudden drop in my uh, water in a tank, especially at the lower layers, which is the green one, layer 4. So, and then when I have sunny days, as such as this one, I see higher temperature in the lower uh, level layers of the water tank. Moving to the next system, which is the space heating with the heat pump. Before running the simulation, I would like to discuss a little bit about the heat pump over here. So if I double click on the heat pump that I have, it's very similar to the other components. So it has its own heat pump catalog. So if you click on this, you can basically select the type of the heat pump that you are interested in. Couple of parameters that you need to take a look at when you are doing this selection. One of them is the heating power. So because it's an air to water heat pump, so what you have here basically is the heating power at 20 degrees C and the 35 degrees C, which is 20.8, for example, this specific type of the heat pump. Then this heating power at air temperature of 10 degrees C and the water temperature at 35, it's 18.7. I usually like this, the heat pump. So when you reduce the temperature, the heating power will be reduced as well. The other point that I would like to mention is not only the heating power, but also, as you know, heat pump, in order to operate, it needs electricity. So if I scroll a little bit to the right, I have electric power. So this time, amount of electricity is basically consumed is gonna be reported in a similar way. So electric power at air temperature of 20 degrees C to water temperature of 35, and then electric power goes to the other, reported in the other temperatures as well. So obviously from these two values, you can calculate the COP, coefficient of the performance for the heat pump. And it's also good to mention that because the heat pump in actual condition and also in the Polysun doesn't work basically in these points, exact on these points, so somewhere in between. So how it works basically, we have to interpolate these values, and Polysun do this for us. So after defining our heat pump, as you can see here, so it could be basically any type of the heat pump that you can select. What you need to do then later basically look at the results. So if we go to the results, first of all, we can start from the system results. So system results, it's going to take a couple of seconds basically as usual. We have to wait for it. And once we have the results, so the results is slightly different from solar systems because the system is different. So we don't have solar system over here. We just run through the heat pump. So, but the parameters almost similar. So we have still, for example, have EOX. So heat generate. So basically, this EOX is electricity that you need to drive the heat pump. And as you can see, it's 2,938 annually, and these values are changing depending on the air source temperature and the working condition. The other thing here that is we already discussed about this is QX. So heat, basically this is the thermal output of the heat pump, and it's 8,401. And it's, again, the values are different depending on the system configurations that we have. We also have, similar to the solar system, QUs and QDEM, which we have already discussed. And what else left here is we can also, for example, if I close this, I can go back to the results and then look at the component results. And now I'm looking at the heat pump results. So now I can see similar results, but with more in more details. And what is interesting maybe for me also to see here is operation time. So here, as you can see, it shows basically to me for how long actually this heat pump is running. So for example, 130 hours, the unit is hour in January, and then values are different depending on my demand and the system configurations. I can also look at the CO2 saving heat pumps, and also I can look at different values as well. If I go back, for example, to the system results, and over here, I can basically find the same values, but with less complexity, I would say. Coming back to the component results again, and then as you can see, I have different values here as well. Coming back to our most complex system, which was basically 10A, the space heating with pool, solar thermal, and also having the boiler. We had hot water demand, space heating, and a pool. So one point I would like to mention here is to discuss a little bit more about the controllers. As you remember, in this system, by clicking on that, we turn off our controller. So if we go back to the concept of the controllers, as you can see, for example, if I move to this controller, I see two blue lines and one red line, which means that the red line shows which component this controller is responsible for controlling. In this case, this boiler. And also the blue lines means where the data or inputs are coming from for this control. So where the information basically coming from. So in this case, it's coming from the tank and also the hot water temperature basically here. If I move to the other one, for example, this one, which is related to the three-way valve. So again, two red lines. So one of them is controlling the three-way valve and the other one controlling the pump for the pool, and the information coming from the tank, the pool, and the solar field. Moving, for example, to this one, the resistance heater in the tank, again, inputs and outputs, inputs, and also which component is controlling. So this one is controlling or auxiliary heating controller, basically, resistant heater, and it's connect, and the information is coming from the hot water side and also the tank. Or I have this one, which is the heating cooling controller, my space heating or cooling controller. In this case, I have two red lines, which one of them is for the pump of the heating loop, and the other one is for this three-way valve, which is also works as a mixing valve. So what basically it does, as you can see, it's received the information from these two pipes as well, and also from the temperature, from the information from the space heating system, and also what I have in the house. Similar to the previous one, I can double click on that, and now I have ability to modify when and how it works. So in this case, it works if it's needed. It could work every day at every hour throughout the year. So you can basically change these values and see how your system could be simulated. I can also, for example, let's run the simulation again. So get the system results for this. So you see that I don't see any error. Similar to what we have done already, if I go to the controller of the boiler here, because it helps the system a lot. So I just, uh, it asks for me if I want to copy, if I want to turn off also for the other ones. I say no, because I would like to maybe turn off for a couple of months and maybe leave it in July on. Now the system is gonna work only in July and during the week, and if it's available. I click OK. And then if I run the simulation, go to the system results, and wait for a couple of seconds to system to give me the simulation results. Now you see that I have an error here, which means that energy demand of the building and the domestic hot water demand not met. So obviously this is not the case. We don't do the system design in this way. I just did it to show you that actually to create an error and show that if you don't think about the importance of the control unit, what should happen. Why it's important? Because, for example, consider you are dealing, as I mentioned before, as an example, holiday houses, so it might not work every day, or even like the places that it's working in a daily basis, like restaurants, and maybe it's closed on Monday, so you don't have it. So you have to define the system based on that. What else? If I open this controller again, I can also see, so I have this help from the lines to see where the inputs are coming from, but I can also see from here the control inputs. So the important information here is that the input is sensor 1 in storage tank, and it's coming from layer 8. So bottom layer, then layer 2, 3, and then top layer is layer 12. As you remember, we mentioned that the storage tank has 12 layers. Also, I can see the other inputs that are optional and coming from the system, and also what is the control unit output is doing. So basically, it's turning on and turning off the boiler that I have over here. As I said, you have also a graphical representation as well for this, so you can always just holding the pointer into the component, you can see the information and the red and blue lines, which shows basically the unit that is controlling and also the input to the controller. This controller can also work in a different way and control the boiler. So we had the variable data as a default, but you can also change to the fixed value. So what's going to happen now? You see two different values here in comparison to the variable, from differential to the cut-in tank temperature and cut-off tank temperature. So how does it works? Basically, it works based on the value that I'm receiving from the input from layer 8 in the tank. So if I open this, just to remind you, I have the bottom layer and then goes, this is slightly one of the highest layer in the tank. What does it mean? It means that when the temperature in layer 8 of the tank is below 50, lower than the 50 degrees C, you turn on the boiler, which means that the controller turn on the boiler and try to heat up the tank. And once I reached 60 degrees C, so if the temperature is above higher than 60 degrees C, what's going to happen at layer 8 of the tank? Then the boiler is going to switch up. And in this case, I'm going to have use the temperature, use the stored energy inside the tank until I get the temperature below 50, and then the boiler is gonna switch on by the controller again. Other controllers also work with a similar principle. So as you can see, look at the controller shape maybe, and also here I have a pump controller which works a little bit differently from the controller that we have already discussed. The principle is similar, but this is basically a differential controller. What does it mean? So similar concept. So control input, as you can see, I have a collector temperature here as an input, and also the pipe 5 temperature basically. So if I even go here and look at that, so I have one input from solar field temperature and the other one from the pipe 5 over here. So what does it mean basically? If I open this, as I said, it's a differential controller, and we're gonna go with a similar concept. So it says here in the cut-in temperature difference, if it's 6, then turn it on, and if it's 4, turn it off. What does it mean? It means that if the collector temperature minus pipe 5 temperature, which is basically the difference, the temperature difference, yeah, it's higher than 6, then turn on the pump of the solar loop. And if the difference between the collector temperature and the pipe 5 temperature is below 4 degrees C, then turn off the solar loop pump. I can also, in this menu over here, I can click on the controller and drag and drop it if I want different controller, and it gives me freedom to pick the controller that I would like to have in my system. So automatically Polysun defines controller, but if you are not happy with them or do want to change them or alternate them with another types of controller, you can select them and do the settings for them. Last, we can move on to the most complex system, maybe with the most complex control unit. So I can go with photovoltaic plus heat generation systems, and I can select one of the systems which works very well. So space, I can go with this one. Space heating, domestic hot water, photovoltaics, it has the inverter. So as you can see, if I open the system, it's going to add it to my system diagram, as I mentioned before. So now what you can see here is the complex controller, the programmable controller. So in here, you can control as an on-off way, but also you can control the logic behind this controller, which I define sometimes MSc project based on this, because this is a field of study, how you match, for example, how you predict the behavior of the households, and then how you program your controller in order to control your system in a more efficient way. These are the most of the things that you're gonna deal when you have your simulation. And now let's move on to the profitability calculations. In order to do the profitability calculation, I created two PV systems, exact same in terms of the number of electricity consumption profiles, the total profile, and the number of the PV modules. Even I changed just only the module type. So this is the photovoltaic module, this is the PV Poly 250. What I'm gonna do now, I'm gonna select my first system, go to the results, go to the profitability calculation. I'm gonna wait a couple of seconds. Now, what's Polysun is gonna do for me is gonna provide me everything that we have almost discussed in our economics session, economics of solar session. So now you see here I have this window for 58 photovoltaics, the first one. I can put the time period, for example. I can put the interest rate as we discussed, inflation, and also important thing is the energy price. So electricity power price, it can't get from the electricity profile over here, or I can even go to the electricity here and put the values. I can get this from my electricity bill most of the time. And then I have to move to the next tab, which is the system cost. So photovoltaic system cost. For this case, I put 2000. And as you can see now that the values have been changed. And service life, I'll discuss this later. You can have a distribute of your components if your components is more complex, storage, planning, etc., etc. Then you go to the next one, which is the operation and maintenance. You can say, for example, maintenance cost per year. So for this one, let's say because it's cheaper, I put maybe 200 pounds per year. I can divide it as a kilowatt hour per year, so annual basically, but I put 200. So 2000 here, and then 200 on the other one. Then I can also define, for example, the interest rate on the debt. If I have some debt, for example, I can put everything here. Then this is the condition for the case A. I can close it, say no. And now I go to my second case, this one. I go to the results again, profitability calculations. And over here, what I'm gonna do, I'm gonna keep the system as it is, same tariffs. Remember in the tariffs that, for example, if you are working in the other countries, these values or these profiles is not gonna work because, for example, it's for Switzerland or for, for, for other areas in Europe, basically. I'm gonna go to the system cost. I'm gonna just imagine in this case, the system cost is slightly higher, 3000. And because it's a high, expensive system as well per unit, then probably maybe my maintenance cost is a little bit higher as well. I would 300 pounds per year. And now I leave the rest is the same as it is. I close this. No. So what I can do to do the comparison between these two systems, I'm gonna have a reference system. So I'm gonna right click on the photovoltaics and then I uh, select this system diagram as a reference. Now it becomes green. So if I go to the results and then now profitability system comparison, what's going to happen? It's going to ask me which kind of the systems I would like to do the comparison. Because only I have two, I can select two. And now what I have here is basically the comparison between these two systems. I can go to the professional report. It's going to ask me if I want to generate it as a PDF. I'm gonna have this as a PDF. I'm gonna wait for a couple of seconds to be created, this PDF file. Once I have the PDF file, now what I can see here, I have these two systems together, and now I have the profitability comparison report here. I can do so. If I go with the more details, which I'm expecting you to do in your assignment, now you're gonna have more in detail calculation and discussion as we did in our session. So this is for making the comparison. And what we need to do now, we need to also think about, so if I go back to my to my profitability calculation for system A, if I have, for example, elements like inverters, etc., then I have to also define the service life here. So for example, if I put a service life of 5 for this, then you have to invest every 5 times for this system. So if I close this now and go to the second system, to the results profitability calculations, because this one was more expensive, for example, I would say service life of 30 year, for example, and which is not true, just for comparison. Then I close this, go to the results and system comparison between these two systems. I'm gonna wait a couple of seconds. I'm gonna generate my professional report. And now the results should be different from what we had in a previous time. So now you see that how it works. So maybe if the lifetime of my system, uh, you know, it's higher, then the value is gonna be different in general. This is uh, the end of the profitability calculation as well. You can get also the energy flow diagrams as well, for example, for your systems. And you can also get your professional report. So if you have just one system, you generate the professional report, and it's gonna basically gives you the most comprehensive types of the report. I'm gonna wait a couple of seconds, get the professional report. That's the comprehensive professional report. So I have the system. We discuss about how we can put our logo or name here. Now the specification of the system, the energy flow, and then you have everything here as well. Then you can also add your profitability calculation over here as well. You can go, for example, to the special reports, do different stuff. So that's it. We reached the end of our Polysun tutorial. I've tried to cover most of the cases. Obviously, there is a plenty of options that you can work with. So yeah, this is the end of our tutorial. Good luck. See you later.